We're continuing our discussion of the spherically distributed charge, and we have a non-uniform charge distribution inside a spherical region, and outside the charge is zero. In part A, we've determined this constant alpha in terms of the total charge contained within the spherical region, and in part B, we used Gauss' law to derive an expression for the electric field in these three different regions. So this was the answer to part A, and part B we found the electric field for R less or equal to capital R over 2 and between R over 2 and R, and also outside this spherical region. Everywhere the electric field is in R hat direction. Now, in part C of this problem, what fraction of the total charge is contained within the region capital R over 2 and capital R? Okay, so we're going to calculate the charge total Q consists of two contributions in between 0 and capital R over 2, and also in between capital R over 2 and capital R. All right, and this charge for R less or equal to capital R over 2 was found before. So let's see. This charge is basically found, the total Q is found by integral rho dV. So between 0 and capital R over 2, we have this integral, and that integral gives us this result, and it's basically 45 capital R cube pi alpha over 480. Now, if we substitute for alpha what we have found, so this part of this integral basically gives us the charge in between 0 and capital R over 2. So if I multiply this by alpha, which is 480q divided by 233 pi r cubes will cancel, 480s will cancel, and I will find 45 over 233q. So that part is known, 45 over 233q, and then we have the charge in the region capital R over 2, R and capital R, and this basically is going to be the charge within this region capital R over 2 and R is 233 minus 45 over 233 Q, and that's basically 0.807 Q. Okay, so that basically answers this question. The question was that we want to know the fraction of total charge contained within the region capital R over 2 and R. All I have to do is to recall the answer to this integral that was calculated in part A, where I can substitute for the result of this integral the value of alpha I have calculated, and I can find the charge between 0 and capital R over 2, and because the total charge is Q, I subtract that from total charge. I obtain the charge contained within this region. So the fraction of the charge is basically 0.807. Let's move on to part D of this problem. Part D asks me the magnitude of the electric field at capital R over 2. Now in part B, I have calculated the electric field for R less or equal to capital R over 2. So if I substitute for the R value here, capital R over 2, I will find the answer I'm looking for. Or I also know the electric field between capital R over 2 and R. If I substitute for R this value, capital R over 2, I should be obtaining the same answer. So there are two ways to go about this. So in part D of this problem, I'm going to evaluate the electric field at magnitude at capital R over 2. The answer I have found is from the first region, 720 divided by 233, kq over capital R to the fourth power R square. Where for R, I'm substituting now capital R over 2, so it will be R square, capital R square over 4, the value that I will substitute. So this will give me 720 divided by 233, Coulomb's constant K, total charge Q, capital R to the fourth power. Then I had R square, and for R square, I'm substituting capital R square over 4. So capital R square will be making the capital R to the fourth power, capital R square at the bottom. So I will obtain my answer to be 180 kq divided by 233 capital R square. So basically this 4 gets rid of the 720 and makes it 180. 180 times 4 is 720. And that's the answer I'm looking for, the magnitude of the electric field at capital R over 2. There's another way, or I can use the electric field I have calculated for the second region, that is this electric field. 480 q over 233 pi epsilon 0 r square. This answer so let's see, this answer was given in terms of K. Here this answer is given in terms of epsilon 0. So in order to convert to K, all you have to do is multiply top and bottom with 4, right? So you would get 1 over 4 pi epsilon 0. And on top here, 4 times 480 will give you 1920. All right, so let's use this electric field magnitude, or E is equal to 1920 kq, k is 1 over 4 pi epsilon 0, 233 times, so now I have r square at the bottom, so that will be capital R square to the fourth power. So this is capital R square divided by 4, sorry. And then the first term here is r cube over 3r capital R cube. Capital R over 2 cubed will give me capital R cube over 8 multiplied by 3 will give me 24. So the first term here is capital R cube divided by 24 capital R cube. minus, and these capital R cubes will cancel. The second term here is R to 5 divided by 5 capital R to 5. So this will give me capital R to 5, because it's capital R over 2 here. 2 to the 5th power is 32. Multiplied with 5 gives me 160. So this will be 160 capital R to the 5th power. So they will cancel. We can see here these will cancel. And the last term is 23 over 1920. So that is minus 23 divided by 1920. And this will give me 1920 times 4kq divided by 232 capital R square. Then I have 1 over 24 minus 1 over 160 minus 23 over 1920. And this gives me 80 times 24 is 1920. 12 times 160 is 1920 minus 23 divided by 1920. So this is multiplied by 80. This is multiplied by 12 to get the common denominator. And this gives me the answer I'm looking for. The electric field at capital R over 2 is 180 K capital Q divided by 233 capital R square. So it's the same answer calculated using the long way. Now let's move on to part E of this problem. Part E: if an electron with charge minus E is released from rest at any point in any of the three regions, the resulting motion will be oscillatory but not simple harmonic. Why? So we need to look at the force the electron will feel in different regions. The force it will feel for R less or equal to capital R over 2 is the electric field at that region multiplied by the charge. The electric field in this region was calculated in part B. This was the answer. So that will be multiplied by the electron charge. So we will have minus 720 K capital Q E R square divided by 233 capital R to the 4th power. If this is the only force the electron feels, it's the mass of the electron multiplied by its radial acceleration. Now you can see that the second derivative of position is proportional to R squared, not to R. So since R double dot is not proportional to minus R, this is not simple harmonic motion. For the other region, the force in the region capital R over 2 and R in between these two, then I substitute the answer I have found in part B again for this electric field in this region multiplied by the charge of the electron. So I will have minus 480 K Q electron charge, capital Q, 233 pi epsilon 0 r square. The first term, r cube over 3 capital R cube minus r to the fifth power divided by 5r to the fifth power minus 23 divided by 1920, and this is mass of the electron times its acceleration. Again, this is not in the form r double dot is equal to minus omega square r, therefore not simple harmonic motion. Okay, and in the region outside of the spherical region, at any point in one of these three regions, for the electron released outside, let's see the force, it will be kq over r squared multiplied by minus e. That's the force it will feel. So force for r greater or equal to r is minus kqe over r square in r hat direction. All right. This is mass of the electron times r double dot. Again, this is not in the form r double dot equals minus omega square r. Therefore, it is not simple harmonic motion. But I see that the force is attractive. It is attractive in all regions of space. Therefore, the motion must be oscillatory. Because wherever the electron travels in these three regions, it is once again it's again going to feel an attractive force. Therefore, the motion will be oscillatory, but the equation of motion is not in the form r double dot equals minus omega square r. Therefore, in none of these three regions, we will observe simple harmonic motion. Okay, to summarize, in part C of the problem, we calculated the fraction of charge between capital R over 2 and R. We already knew the answer for R less or equal to capital R over 2, 45 over 233Q. This was found in part A in the alpha calculation. The charge in that region is integral rho dV. The result of this integral can be seen here. And if we substitute for alpha this value, we can get this result, 45 over 233 capital Q. Since the total charge is capital Q, the fraction of the charge is 233 minus 45 divided by 233, 0.807. In part D, we were asked to calculate the magnitude of the electric field as capital R over 2, which can be found either by substituting R equals capital R over 2 for the solution in the first region or the solution in the second region. They give identical results as expected. In part E, for all three regions in space, we calculate the force an electron would feel when it enters that region. So if it is released from rest at any point in any of these three regions, the resulting motion will be oscillatory because it's going to feel an attractive force. So because of this minus sign here, it's going to be an attractive force. It's in minus r hat direction. So if the electron moves in space from r equals 0 to some negative r value, it feels an attractive force towards r equals 0. If it moves to some positive r value, it feels an attractive force towards r equals 0. So therefore, it's going to be oscillatory motion, but the equation of motion is not in the form r double dot equals minus omega square r, as shown in all three regions in space. Therefore, oscillatory but not simple harmonic motion.